Hello students, let us review the mechanism tutorial question 1. Okay, so if you take a look at 1a, you will notice that the configuration of the chiral center is inverted. How do we know? Okay, so the first thing is this is the substituent, Br, of the reactants, and then the substituent at the products is the ethoxy group or OET groups. Okay, then if you take a look at the chiral center, you notice that the methyl group and the H swap in positions. Yeah, so this is clearly an indication that an inversion of stereochemistry occurs. Yeah, it will not be wise to simply look at the RS configuration. The reason being the RS configuration do change depending on the nature of how you assign the priority to the substituents. Okay, so it is possible that even though there is an inversion of stereochemistry, the way you name the chiral center, it could go from R to R instead of R to S or S to R. Yeah, so looking at the RS configuration alone might not be a good indication to see whether there's an inversion. So the best way to look at inversion is to place the chiral center side by side and then the rest of the groups in place, and then you see whether there's a swap in two of the key groups which you are comfortable in looking at. Yeah, so with all this in place, now let us attempt to draw the mechanism, because it's quite clear that there is an inversion of stereochemistry. Okay, so therefore the first thing we can conclude is that 1A undergoes SN2. Okay, we must be very clear about this. Okay, it undergoes SN2. So if it undergoes SN2, so that means that the O ethyl group, right, will approach from the rear of the CBr bond. Okay, so you need to draw it from the rear, and then in the process the bond breaks towards the Br. Okay, so if you want to draw in the transition states, it should be drawn clearly. So in this case, the transition state should be drawn like this. Okay, so you can just follow whatever you are given. You do not need to rotate anything or change anything. Okay, so remember to put in a dotted line, dot 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 Br, and then dots 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 dot dots OET. Okay, so something like this, I think it's okay. Of course, if you are very strict about it, then obviously you might want to rotate the ester group away from the incoming nucleophile, but I think it is fine for now, because the emphasis of this question is not so much on the drawing of the mechanism alone, but the drawing of mechanism coupled with an explanation why do you get certain product. I think that is the main focus of the question. Yeah. Then after that, you would notice that after drawing the mechanism, your products would look like this. Okay, so you have an ester group, and then so because there's an inversion, so the methyl group will be pointing downwards, and then the H will be projecting away from you, and then of course the OET group is here. Yeah, you notice that what I've drawn here in green, right, is a little bit different from what was given to me here. Yeah, but you can easily convert them, because they are identical, by simply doing a bond rotation. Okay, that should be a bond rotation of 180 degrees. Yeah, then the methyl group that's pointing towards you will now be pointing away from you. The H that's pointing away from you will now be pointing towards you. Yeah, so this is purely an SN2 mechanism, so I hope it's clear from the explanation. Next, we'll move on to 1B. Okay, so for 1B, right, again, what you have is something similar. Okay, so in terms of the chiral center, it looks the same, except that there is a little change. The substituent now is an OET group, an O ethyl group. Okay, then you notice that in the course of the reaction, there's a retention of the chiral center, and then there's an inversion as well. Okay, so how can we make sense out of this? Yeah, and of course from here you get 50-50% mix, so therefore you should roughly have an idea that the reaction simply undergoes an SN1 mechanism. Okay, so this should be an SN1. Yeah, so one of the mistake that most of the students make when they drew this mechanism is they simply just let the CBr bond break. And then they simply work with this particular carbocation, which looks like this. Okay, so the H is projecting in, and then the methyl group is projecting out towards you, and then with a plus charge. Now do take note that this particular carbocation is not stable because it is bonded directly to a highly electronegative oxygen atom. Yeah, and at the same time the carbon has only 6 electrons around it. So the highly electron deficient carbocationic center, if it's bonded to an electronegative atom, it's definitely not going to be the most stable form. So you shouldn't be drawing this form. Instead, you should be drawing the resonance form. So the lone pair will actually delocalize and then form a pi bond over here. And then now the oxygen will take on the positive former charge or the +1 charge. And then you form something like this. Okay. Regardless of whether you're looking at the structure on the left, the resonance structures on the left, or the resonance structure on the right, the geometry around the carbon center is trigonal planar. Yeah, so because of this, I think you can easily continue the mechanism. If the O methyl group approaches from the top plane, so you have to draw in from the top plane, and then the pi bond will break towards the oxygen to neutralize the charge. Or you can draw it approaching from the bottom plane as well. I think you have to draw both in. Okay, so attacking from here, and then now the pi bond breaks towards the oxygen. Yeah, so you have to draw both the top and bottom attack. Okay, and in the process, you should draw out the structure. So in this case, the carbon now projecting upwards. Then the Me is here, and then the O methyl group is here. Okay, and then for the tops, it's like this. You guys should be quite familiar with this. It's not something that is very new to you because you have seen it, I think, a few times. Number one is in electrophilic addition, where if your carbocation is bonded to 3 different groups, then the nucleophile can approach it from the top and bottom plane with near equal probability. And then that will be the same instance when you look at it from the SN1 mechanism. Yeah, so in our case here, it is still an SN1 mechanism. The only difference is that now the carbocation will take on a more stable form, which is this particular form. Why is this the more stable form? Because all the atom, of course, except the H, has the octet configuration. Yeah, so again, whenever stabilization is possible, it will prefer to be stabilized. Yeah, then so after a while, if you are more experienced, when you are looking at a system like this, right, then you are probably going to draw the mechanism straight away by pushing out the Br by forming the CO pi bond like this. Okay, so when you're more experienced, you can draw what I have drawn in red. Yeah, because you know that the presence of a highly electronegative oxygen or even nitrogen, right, will allow the pi bond to be formed between carbon and oxygen, and in the process kick out a good living group. Yeah, so the good living group in this case is bromides. Yeah, then if we move on to part C, okay, it's a bit interesting here for part C. Yeah, so you'll notice that if you just take a look at the substituent, right, so it's Br here, and then I have a OH minus nucleophile. Yeah, so now the OH minus nucleophile is being substituted in place of Br. So from here, it seems to imply that I'm not saying that this is the correct mechanism, okay? So it seems to imply that the OH minus group seems to come from the front, okay? And then you kick out like that. But you know that this is impossible because based on the mechanism you have learned, regardless of whether is it SN2 or SN1, yeah, you know that mechanism are orbital controlled. So for SN2, we stress to you that it must be a rear attack. And then in this case, it can't be SN1 because if it's SN1, it will not be 100% of one stereoisomer. Yeah, so you know that if you have drawn something like this, then it's incorrect. Yeah, so if it's incorrect, then you need to probably modify your mechanism a little bit. Yeah, not to draw the one I have just drawn. Okay, then you also notice that I have a unique group here, which is a thio. Okay, so if you go check up on your thiol, right, you notice that the thiol group is pretty acidic. Okay, so in this case, if I have a OH minus, the first thing that could probably happen to my thiol group, right, is that it will be deprotonated. Okay, so I'm going to just draw it in first. Yeah, so the OH minus will probably deprotonate my thiol first, okay, to give me the thiolates. Okay, so the thiolate will now have a negative charge, which allows what we call an internal nucleophilic substitution to take place. Okay, which looks like this. And then in the process, it will produce a 3-membered ring, which is highly strained. Then the highly strained 3-membered ring, right, will of course encourage a nucleophilic attack by the OH minus, by the hydroxide nucleophile, from the rear of the CS bond like this. Okay, and then it will break towards the S. Yeah, so whenever you show a mechanism, right, it will be good if you can show it as close to the actual mechanism as possible. So in this case, the rear attack from behind the CS bond. Okay, and then in the process, what I'm going to get is a ring opening process. So the ring will open. Okay, and then I'm going to get an OH here. Okay, and then of course the sulfur, okay, will be over here with a negative charge. Yeah, then because of the deprotonation earlier on, yeah, so there's this deprotonation, right? Yeah, so the lone pairs on the sulfur can now grab a protonic hydrogen from water and then regenerate the OH minus, and then I'm going to get the products. Yeah, something like this. Yeah. Some of the students might ask, what if I am not aware that thiol is more acidic than an alcohol and it can be deprotonated by hydroxide? So what can I do? Yeah, so that is not a problem at all. If you didn't know of this particular fact, you can simply just perform an internal SN2. So let me just show you very briefly. So it is perfectly fine if you just attack directly like this. Yeah, and then after that, the OH minus will then grab the H bonded to the sulfur. Yeah, because if it undergoes the reaction like this, right, so it is likely that my sulfur will have a +1 formal charge due to the hydrogen. So it will be like the conjugate base, sorry, conjugate acid. Yeah, so this H can be easily deprotonated. Okay, so you don't really need to worry. Again, as I often mention, your job is not to draw the most correct mechanism. Yeah, but you should be proposing the most likely mechanism in the reaction or in the reaction scheme you are being asked to draw. Okay, yeah, so with that, we are done with question 1. I hope everything's going on well with question 1. Then if not, next, we'll move on to question 2, which is also a relatively interesting question. Okay, so for question 2, you are asked to account for the observation that the slow rate of hydrolysis of a primary chloroalkane can be markedly increased by adding a small amount of Ki. So obviously, this particular reaction takes place in an aqueous medium. Yep, and take note that it's very, very slow if you simply just involved chloropropane and water, but the reaction rate will accelerate if you increase, or rather if you add potassium iodide into the solution. Yeah, so the first thing I think we need to come to terms with is that H2O is the nucleophile. Okay, so it's the key nucleophile we have in this particular system. Yeah. So in some of the scripts, or in quite a number of scripts which we have marked, we notice that students use hydroxide as the nucleophile. Yeah, take note that this is incorrect, because how can I generate hydroxide between H2O and say Ki? Remember that Ki, right, is an ionic compound. It's an ionic compound. Yeah, so in aqueous medium, what you're going to have here is simply K plus aqueous and I minus aqueous, which is iodide aqueous. Yeah, so iodide being the conjugate base of a very strong acid, which is HI, will never be able to generate OH minus when it reacts with water. In fact, I minus will simply be solvated by water, but it will not undergo hydrolysis with water. Yeah. So remember some of the things you have learned from acid-base equilibrium is very, very important. Okay, so this being a conjugate base of a very strong acid, okay, so it will not be hydrolyzed. Remember this. Okay. Yeah. So in this case, how can we make sense of the reaction? Yeah, I think we can make sense of why is it slow. Okay, so it is slow because number one, we have a very poor nucleophile. So water in this case is a poor nucleophile. Yeah, so you have to emphasize that water is a poor nucleophile. That explains why the first reaction is very slow. Yeah, and the reason why the second reaction becomes fast is because I expect iodides, right, to be a stronger nucleophile than water. Okay, so again, iodide is a stronger nucleophile than water. So when I add in iodides, what is going to happen is that the iodide will undergo or will perform a nucleophilic attack on the chloride. So in this case, it will attack from the rear, okay, and then the C-cell bond will break. And in the process, I'm producing the iodopropane, of course, plus Cl minus. Yeah, and iodopropane, right, as all of you know, because iodine is a good leaving group. Yeah, so because iodine is a good leaving group, a poor nucleophile, such as water, right, will be able to attack it from the rear again and then cause iodide to leave. Yeah, so I think after a while you should be able to get the correct thinking of mechanism in the right place lah. So for example, if I have a poor leaving group and then I have a weak nucleophile, then obviously the reaction will take a long time. Then how can I accelerate the reaction? Okay, I can accelerate the reaction by doing two things. First, I can make the nucleophile a stronger nucleophile. So instead of water, I can use OH minus. Yeah, but in this case, I do not have OH minus. Yeah, so if I do not have OH minus, what do? Then I'll make chloride a better leaving group. How can I make chloride a better leaving group? By replacing it with the better leaving group in this case. But the better leaving group also tends to be a poor nucleophile. So in this case, we have the best of both worlds because iodide is itself being highly polarizable, right, is a better nucleophile than water. So in this case, iodide can replace Cl, but because the Ci bond is weaker than the CCl bond, so that makes the bond being more easily broken, and iodide is a good leaving group as well. So this particular reaction will take place when water will displace iodides. Okay, so in the process, I'm going to generate the conjugate acid of the required alcohol. And of course, the next step is obvious because the OH bond will simply be broken, will probably be grabbed by a water molecule, and then in the process, I'm going to produce propane 1-ol. Okay, so if you look at if I attempt to draw the energy profile diagram, I think it will be much clearer to you. So in the energy profile diagram, right, we have energy here, okay, and then we have reaction coordinates. Yeah, so let's say we have let's say in our case here, right, we have a good leaving group. So we have a leaving group here. I just put Lg as a leaving group. Okay, yeah, then if I'm going to allow nucleophilic substitution to take place with, let's say, the iodo, yeah, then it will probably look something like this lah. So the profile diagram will go up and then it will come down like this. Okay, so this is the one where I'm going to get iodo here and then plus the leaving group. Okay, then we can look at another pathway where I'm going to use chloride as the nucleophile. Okay, but obviously the activation barrier will be higher. Okay, and then but CCl bond is stronger. So in this case, I'm going to get Cl here and the leaving group here. Okay, so you'll notice that iodides being a better nucleophile, yeah, will have a lower activation barrier leading to the products. So this is the EA. Okay, but of course the CI bond is weaker lah. So if you consider the reverse reaction, obviously it will have a lower activation barrier as compared to that between the chloroalkane and the leaving group. Yeah. Okay, so with that, we have come to the end of the debrief to question 2. Yeah, so we're going to move on to question 3. Yeah, for question 3, right, we have this particular Nobel winning work by Barry Sharpless. Okay, so it is for his breakthrough in asymmetric oxidation. Yeah, he is using this particular complex, titanium complex, known as this titanium complex, okay, with a chiral diisopropyl tartrates, okay, and then of course the subsequent oxidizing agent is tertiary butyl hydroperoxide. Yeah, so this is just represented by DIPT in short. Okay, so whether it take on plus or minus. Yeah, so if it approaches from the top, then it's going to deliver oxygen on the top of this cartoon or this particular diagram. Yeah, so if it approaches from the bottom, then it will approach it, it will insert oxygen onto the bottom. Yeah. So now the question is, when S undergoes the reaction above, with an unknown configuration, epoxide T is obtained in the reaction scheme below. You are asked to suggest the configuration of DIPT used. So basically your answer is either plus DIPT or minus. Okay, so it's a 50-50% chance of getting correct. Yeah, because it's a 50-50% chance, as you know, most of the time, we don't give credits to guesswork, so you have to explain how you obtain your answer. Okay, so how do we obtain our answer? I think first of all, we need to fit S into the cartoon above. Yeah. So how do we fit S into the cartoon above? So first we will do a bond rotation. Sorry, not bond rotation. We'll rotate the molecule 90 degrees. Yeah, so we just rotate 90 degrees. Okay, so when we rotate it 90 degrees, it will look like this, and then like this, and then like this, like this, and then like this. Okay. Oh, sorry. So the top is actually a H. Yeah, so like this. So this is how it looks like when we rotate it 90 degrees. Okay, so 90 degrees. Oh, sorry. Carbon 2 have another bond. Yeah. So we'll rotate it 90 degrees. This is how it looks like. But you'll notice that if I compare between the structure I've drawn in blue and the diagram above, right, it doesn't fit. Yeah, because I need to fit the CH2OH into this particular side. So I need to fit it into this side. Yeah, in order for me to predict the correct catalyst. Okay, or rather to predict the catalyst with the correct configuration. Yeah, so in this case, right, in order to fit, I need to do a bond rotation. I need to do a flip. Okay, 180 degrees flip into the plane of the paper. Yeah, so when I do that, I'm going to end up with something like this. Okay, like this, and like this. Okay, so again, this is 2 and this is 1. Yeah, so after doing this, right, now you can see that this essentially is R2. Okay, so this is R1. Okay, and the H here, so there's a H here, which I didn't draw out. So this is essentially R3. Then the next thing I'm going to do is to rotate T as well. Okay, so we'll do the same thing, rotate 90 degrees and then flip it into the plane of the paper. Yeah, so we're going to end up with something like this. I'm going to just draw it out very quickly. We're going to end up with like this, like this, like this, OH, and then so this is carbon 1, this is carbon 2, and then of course the like this, and then like this. Okay, and then of course we have the groups projecting upwards. The epoxy oxygen is now projecting upwards. Yeah, then now I'm going to compare these two, so the structure here as well as the structure here. Yeah, so you notice that because now the epoxy oxygen is pointing upwards, so I should be using plus DIPT. Yeah, so it's as simple as that. Of course, when you explain to the examiner, all you need to do is simply just draw this out, and then if you can identify R1, R2, and R3, and then point to the examiner that compound T, if you flip it into the same configuration or the same conformation in that sense, you have the epoxy oxygen pointing upwards. So therefore, in order for the epoxy oxygen to be pointing upwards, the DIPT will have to approach from the top, and therefore I should be using plus DIPT instead of minus DIPT. Yeah, so any reasonable explanation will work, right? Then we'll move on to part B. Okay, so now part B, we were told that when epoxides are subjected to sodium hydroxide solution, the epoxide ring will open and a diol will be obtained in the reaction scheme shown below. Okay, so when epoxide T is subjected to sodium hydroxide, two products are possible. One of the products, W, has RS configuration. Okay, so let us take note of this. RS configuration at C1 and C2 respectively. Okay, so now the first thing we need to do is I think we need to redraw T. Yeah, so if I'm going to draw T, right, T will actually look like this. Okay, projecting inwards like this. Okay, one of the mistake, I would say mistake lah. One of the common thing which most of the students do, right, is they tend to draw the mechanism directly following what we have drawn for you lah. So a lot of students actually draw the mechanism like this, and then the ring will open, and then what they're going to end up with is something like this, O minus, and then they have something like OH here. Yeah, so there is actually nothing wrong in drawing the mechanism like this, except that it's very difficult to see the rear attack. Yeah, because if you take a look at parts B2, right, question says it's SN2 like fashion. So when they wrote SN2 like, it is really important for the students to recognize that they have to draw a rear attack to the best of their ability, of course. Yeah. Okay, I'm actually jump starting like from I haven't done B1 yet, so I'm just going to just showcase to you that eventually the SN2 mechanism will lead to W and something else, which is another product, because later on you need to suggest how the other products may be obtained. And then of course here you know that I can the hydroxide can either attack carbon 1 or carbon 2. Okay, so carbon 1 is a tertiary carbon, carbon 2 is a secondary carbon. Yeah, so being SN2, hydroxide will prefer to attack carbon 2 rather than carbon 1. Okay, yeah. So in this case, I think the easiest way is simply just draw out the mechanism, and then perhaps get the product out first before we do B part 1. Yeah, I thought that would be the easier approach lah. But if you want, you can simply just draw the product out and then try to predict the configuration, and then if you get the correct configuration, then that will be W lah. If you get the opposite, then you just swap the relevant stereochemistry around, and then you should be able to get the correct answer for parts 1. Okay, yeah. And then I'm going to introduce you to another method or another perspective for you to draw such mechanism in a slightly more elegant manner. So what you can do is, I'm going to show you a different perspective of looking at this particular structure. Okay, so that eventually you end up with a relatively nice staggered configuration as you draw your mechanism. Okay, yeah. So what I'm going to do is I'm going to showcase to you the epoxide taking on the plane of this paper like this. Okay, so this is carbon 1 and this is carbon number 2. Okay, and then because this is carbon number 1, what I'm going to do is the methyl group will now be projecting into the paper, and then the OH, or rather the CH2OH group, will now be projecting out. Okay, and then of course let me see, the H will now be projecting in. Okay, the ethyl group will project in, and then the H will project out. Okay, so I'm going to showcase to you maybe one of the perspective you can take when you draw such mechanism, because if you look at it this way, right, it's easier for you to draw out your mechanism to showcase the real attack. Okay, then after that, what I'm going to do is I have a hydroxide here. Okay, so I'm going to attack carbon number 2, and then the ring will open. Okay, so when I attack carbon number 2, the ring open, right? I'm going to end up with this OH. Okay, this is carbon number 2, carbon number 1, O minus. Okay, then project in, project out. Okay, and then the H like this, and then like this. Okay, and then of course this will then undergo acid-base neutralization with H2O. Okay, to get the product. So my product, I'm going to find a space to draw. So maybe I'll draw it below here. Okay, I'm just going to draw it below because there's no space. Okay, like this. So I'm going to draw it like this. So this carbon 2, 1, OH, projecting in, projecting out, OH, in and out. Okay, so this is one product. Another potential product I can draw is my hydroxide can now approach from carbon number 1, and then the ring will open. Okay, so I'm not going to draw the intermediate alkoxide. I'm just going to simply draw the final products out like this, like this, like this, OH, and then projecting in, projecting out, OH, and then H here, and then like this. Okay, so this is carbon number 2 and carbon number 1. Okay, so if you try to label the RS configuration over here, yeah, then let's try to do that. So carbon number 2, the H is projecting towards me. Okay, so it's the lowest priority. So the highest priority is the oxygen here. Okay, so this is priority 1, and then the right hand side, this will be priority 2, and then 3, right? So 1, 2, 3 in a clockwise manner. Okay, but because hydrogen is projecting towards me, yeah, so if I look from the back, it will be anti-clockwise. So carbon number 2 will take on the S configuration. Okay, so I'm going to erase this first. Okay, carbon number 2, S configuration. Next, we're going to look at carbon number 1. So O will take on first priority, and then CH3 is likely to be the lowest priority. And then over here, we have CH2OH. So the other one, carbon number 2, will be carbon as well. Yeah, but because they share the same atom, so we're going to need to look at the next level. So the next level will be O, H, H. Okay, and then for carbon number 2, it will be O, C, and H. Yeah, so there's a differentiating one at the second counts. Okay, so in this case, carbon is the differentiating one. Okay, so carbon number 2 will take on a higher priority. So this is second priority. This will be the third priority. Yeah, so lowest priority group pointing away from us. So this will be a clockwise. So we'll take on R configuration. Yeah, so if you take a look at the question, W has R configuration at C1, S configuration at C2. Yeah, so this will be my W. Okay, so yep, we have answer B part 1. So my W is the structure in red. We have also answer B part 2 because we have drawn for you the mechanism giving us W in red, and then of course the other stereoisomers in blue. Okay, then in B part 3 suggests if W is the major products. Briefly explain why. Yeah, so W is not the major products. Yeah, as what we have seen above, because carbon number 1 is the tertiary carbon, carbon number 2 is a secondary carbon. Yeah, so because of that, carbon number 1 is more sterically hindered as compared to carbon number 2. Yeah, so in that case, SN2 will not be preferred at carbon number 1. Yeah, so therefore W is not the major products. Okay, so not the major products. Okay, next for part 4, you are supposed to suggest a suitable starting material to obtain the other diastereomer of T, keeping the reaction conditions configuration the same. So we're going to use plus DIPT. Yeah, so for me to get the other diastereomer, yeah, so that means that instead of, maybe we'll make it easier. So I'm going to get, this like this, maybe. Oh, yeah, so remember that for diastereomer, only one of the chiral center changes. Yeah, then if I'm going to use the same DIPT, that means that the DIPT must come from the bottom, right? Yeah, but of course, if we fit it into this cartoon, it will come from the top. Yeah, so because of that, then therefore my starting material will look like this. Okay, so this will be the answer. Yeah, so this will be the compound I will use to produce the other diastereomer of T. Yeah, I hope that's okay. Yeah, so this is the simplest and fastest way to come out with the answer. Okay, so that will be the end for question 3. Next, we'll look at question 4. Okay, question 4 is a relatively interesting question where you have a computational studies being done on an idealized SN2 reaction. Okay, between ammonia and chloromethane, modeled under different conditions. So you have gaseous states, cyclohexane and DMSO. If you recall from solvent effects, you know that cyclohexane is an example of a non-polar aprotic solvent. Okay, and then DMSO is an example of a polar aprotic solvent. Okay, so in the presence of different solvent, the potential energy was calculated, plotted against the coordination coordinates, which is given by the pyramidalization angle. That's quite a mouthful, okay? Pyramidalization angle. Yep, okay, so I think there are a few things we need to understand from this particular energy profile diagram. So maybe we'll work on it a little bit slowly. So first of all, right, we need to understand that the starting point is almost the same, okay, but the ending point is a bit different. Okay, so obviously we can sort of understand why the ending point is different, because number one, right, let us look at the reaction. Number one is my starting reagents, they are all uncharged. Okay, that means they are neutral, but my product is charged. Okay, so it is thus understandable that if my product is charged, they will be better stabilized in a polar solvent. Yeah, so in this case, DMSO is able to better stabilize my charged products as compared to, let's say, in cyclohexane or in the gaseous phase. Yeah, then why is it that cyclohexane is better? Well, I mean, cyclohexane is some form of solvent that can form dispersion forces or instantaneous dipole-induced dipole interaction, at least with the non-polar electron cloud. So there is some form of stabilization, a bit. Yeah, so that's why you can see the stabilization. It's not so good. It's about the same as what you have at the beginning, but better than nothing. And of course, in the gaseous phase, is the most unstable because the two charged species are far apart. Okay, then another thing we need to understand is what exactly is pyramidalization angle. Okay, so this particular angle, right, if you just take a look at this particular diagram, it goes from like minus 19 degrees to about 19 degrees. Okay, then so that is something which we need to ponder about, because for part A we will ask, from the information above, right, explain what is meant by pyramidalization angle. So we will ask to explain what is it. Okay, so if you look at the transition state, the transition state is actually takes on what we call a trigonal bipyramidal geometry. Yeah, so this is like an ideal SN2 reaction. So that ideal reaction means that the bond breaking and the bond forming is being established to the same extent, and then in the transition states it is a perfect trigonal bipyramid structure. Yeah. So from here, I think you can see that this is a trigonal plane. Okay, it's a trigonal plane, and then of course this is the axis lah. Yeah. So you notice that over here, right, we have a 0 degree. So this is like the ideal, and then you can see how the TS actually changes. Okay, so it goes from like an early transition state to for the rest will be like a late transition state. Okay, then I think from here you can sort of understand that the pyramidalization angle, right, will be reflected by the distortion. Okay, by the distortion of the trigonal plane, especially in this case, in our case here is we are talking about the CH3 here. Yeah, so how the CH3, right, is being distorted or is being deformed with respect to the trigonal planar geometry in the middle of the transition states. Okay, so therefore we are actually looking at this particular angle. Yeah, but of course for an idealized transition state, the distortion angle is 0 degrees lah. Yeah, because it is not distorted. But in our case here, so let's say we draw the thing in, right? So it is sort of distorted by a little bit. So this distortion maybe as reflected here is about minus 19 degrees. Okay, and then of course the product is plus 19. Okay, yeah. So with that little bit of understanding, I think you can actually suggest what the pyramidalization angle is. Although some of us, I mean some of you actually wrote quite interesting things. I mean, you were trying to discuss how the nucleophile attack and how it causes the bond, the leaving group bond to be distorted. But the leaving group bond is not distorted because the nucleophile and the leaving group, they are orthogonal to the trigonal planar geometry. Yeah, so it's a bit difficult to talk about the distortion with respect to the nucleophile and the leaving group. Yeah, so it might be easier for you to take reference from the trigonal plane in the trigonal bipyramidal transition states. Yeah, and how the starting material and the product is it's different, or it's being distorted from it. Yeah. Okay. Then for part B, describe the trend in the enthalpy change of reaction under different conditions. So briefly explain the trend or the shift in transition states along the reaction coordinate under different condition. Okay. So you are being specifically asked to describe the trend in enthalpy change under different conditions. So what you can say is that from gas to cyclohexane to dimethyl sulfoxide, right? It become increasingly more exothermic. Or if you prefer to go the other way around, for dimethyl sulfoxide to cyclohexane to gas, right? It becomes increasingly more endothermic. Yeah. A poor answer will be saying that enthalpy change become bigger or smaller, or become greater or smaller. Yeah, all this answer shouldn't be included in, because enthalpy change has a sign. Yeah, so you have to emphasize whether is it more endo or less exo. Yeah, and then briefly explain the shift in transition state along the reaction coordinates. So explain the shift in transition state. Okay, so when it's in dimethyl sulfoxide, is actually an early transition state. So the early transition state will resemble the starting material more. Yeah, but for cyclohexane, or when the reaction takes place in cyclohexane or in the gaseous phase, it is more of a late transition state. So therefore, they will resemble, the transition state will resemble the products more than the reactant. Okay, yeah. Then moving on to part C, by considering the effect of the solvents account for the trend in the enthalpy change of reactions under the different observed conditions. Okay, I think we have already answered this part. Yeah, so because in the course of SN2, a charge is being developed in the product. Yeah, so therefore the product is better stabilized by a polar solvent such as DMSO. and the stabilization is due to the formation of ion-dipole interaction. Yeah, and then earlier on we said that for cyclohexane, my charged product also has a non-polar methyl group, so it can form some form of dispersion forces with the solvents. Yeah, but of course it's not sufficient enough for the reaction to turn exothermic. Yeah, because ion-dipole interaction obviously is much stronger than dispersion forces in this case. Okay, then in the case of the reaction taking place in the gaseous phase, there is no stabilization experienced. Okay, then for part D is the part where most of the students didn't get it so correctly. You're supposed to sketch the transition state between ammonia and cyclohexane in the gaseous states and in DMSO. So we're looking at the two extremes. Show clearly the relative difference in bond length, position of atoms, as well as indicate relative size of the charged being developed. Okay, so we'll just take this as a reference. Okay, so number one, right? If we try to draw it for DMSO, okay, I think it is very clear that it is an early transition state. So if it's an early transition state, it will resemble more of this. Okay, so we'll try to sketch that out. Okay, so for early transition states, the carbon-nitrogen bond is not exactly formed very well, and then CCl bond is a little bit broken. Okay, and then for this portion, we shouldn't be drawing a trigonal plane. We should show a little bit of distortion to the left-hand side. Okay, why is that the case? Well, because remember that it resembles the starting material. Yeah, and because this bond is not perfectly formed yet. Yeah, remember that we can take reference from the pyramidalization angle. So it's actually a negative value. So therefore the distortion is more to the left. Okay, so there will be a transition state. Okay, this is a transition state. Okay, and because it is in DMSO, right? So I expect the charge to be quite stabilized, and of course the reaction is not even close to completion. So this charge will be just slightly developed, and this nitrogen will develop a slight positive charge. Okay, very slight. Okay, not even close to completion. Yeah, so it's shown by the size of my delta plus. Okay, then on the other hand, if I'm going to draw it in the gaseous phase, it is very close to completion. Okay, so therefore I'm going to draw it more, I mean it resembles more of the products. Okay, so something like this, like this, like this, and then the edge is like this. Okay, so I'm going to put a huge delta plus here. Okay, and then of course the CCl bond will be very, very far apart. Okay, because it is almost breaking away, and then I'm going to put a huge delta minus. Okay, something like this. Okay, so you'll notice the difference between the two transition states. One has a positive pyramidalization angle. Okay, the one in orange. Then the one in green has a negative pyramidalization angle. Yeah, because the one in orange resembles more of the products. The one in green resembles more of the starting material. Okay, then the last part. When methanol was used as a solvent instead of DMSO, the rate of SN2 was found to decrease significantly. Okay, remember that methanol is a polar, protic solvent. So that means that methanol is able to form hydrogen bonds via its platonic hydrogen. Yeah, in this case, because our product is charged, so I think it is better to say that it's able to form a significant ion dipole interaction, okay, with the products. Yeah, but at the same time, let us not forget that methanol, right, being a polar protic solvent, it's able to stabilize the ammonia significantly more than that in DMSO. Yeah, so if I look at methanol, maybe the starting point can be found here. Yeah, so you'll notice that the activation barrier it's a lot higher than that when it's solvated in DMSO. Okay, so in this case, because of the increase in activation barrier, it leads to a reduction in the rates of reaction. Yeah, so remember always that a protic solvent solvates the nucleophile well. And because the nucleophile is well solvated, the lone pairs of electrons will not be that available to coordinate or to perform its role as the nucleophile to approach the electron deficient carbon center. Yeah, so that is the benefits, or rather the stabilization being imposed by the polar protic solvent. Right, so that will be the end of the review for question 4.